All right, this is part two, continuing midterm one review. We're going to start with question number 7. We left off with 6 in the last recording. So number 7. Also, like the camera situation got worse. Like it's as if we're looking down, but I guess now we all get to experience what it's like to be tall. Okay, so here we have a particle Q. That's this position right here, and we have it moving in circular. Oh yeah, okay. We have it moving in this circular orbit, right? So at any one moment, its actual velocity, is tangential to that circular direction there. And we're told we're given the radius r and a constant magnetic field. The first thing we want to do is determine the speed of the particle, and we're going to find the speed. Well, we're going to find that through Newton's second law here, okay? So we need to establish a few things. So we're used to seeing this now, F, equals the mass times acceleration. Like this should be old news at this point. But what's really the force acting here? And it requires, to answer that question, you need to make kind of an inference and kind of work in the other direction. So the force acting here is actually a magnetic force, FB, towards the center of the circle. And it kind of requires you make an assumption, because otherwise, like without this force, this particle will just shoot in a straight line, right? Like there's nothing holding it and causing it to go in that circular orbit. But because there's that constant force that, and in conjunction with this velocity here, it's going to kind of move around in the circle, right? So there is a force working there. And now we need to also determine the direction of the magnetic field. Okay, so we have to do the right-hand rule number 1, this whole business, but with a modification. That being, we know the direction of the force, so we start with our thumb now. We know the direction of the velocity, and we have that B field coming out of the page, right? So we kind of work backwards here to say that B is coming out of the page. And again, there needs to be that force towards the center of the circle. Otherwise, that particle will just shoot in a straight line there. Okay. So we'll say FB equals ma. Not just any acceleration, it's centripetal acceleration. We're going in a circle here. And if we recall from last semester, AC is equal to v squared over r. So therefore, we can clean up this equation a little bit, and we can say m, of the oh, they don't tell us what it is. It's like mass of the charge, and then v squared over r. This FB, we know the equation of. It's QV cross B. It's a cross product. QV cross B. I'm going to skip the whole sign business, but again, our velocity and our B vector are perpendicular, right? The B vector is like coming straight out, so there's a 90-degree angle between them. So I'll cancel out one of these V's, cancel out one of those V's, and I see my variable of interest, that velocity, on that side of the equation. So I'm just going to rearrange some things, clean it up as needed, and I'll say my V is equal to QBR divided by the mass. Okay, that's the velocity. Now, in part 2, we're asked to determine the magnetic field produced by the charged particle at the center of the circle. Well, if we're going, it's going to be like a little flip here, right? It's coming out of the page on the outside, so we're going to be going in on the inside. You can already say that. And then in part B, we're going to be dealing with this equation for a charged particle. It goes mu naught Q B cross R. I'll do lowercase r actually. R, both of these are vectors, divided by 4 pi r squared. Okay? And we know it's going out into the page now, right? It was going out before, so I'll just say okay. And you can still see it the whole way over there, right? Yeah. And something that's important about this equation is what this r really is. This r tells you more about, a direction. And it's not truly like an r variable, right? So I can't cross off this squared here and cross that guy off. Because they're different things. They're different things. That's like the R vector, and it tells us how to orient it in a right-hand rule, right? Here, let me pause and let me double check the name of that kind of variable. All right, sorry, it's called a unit vector, right? And like I said, it has no actual value. It's actually this whole thing in parentheses is equal to, here, I'll write it over here. So V cross R of these vectors is equal to V sine theta, where that theta is normally equal to 90, right? And it helps you determine that direction where you it basically helps you solve in the right hand rule to determine the direction of the field. And we can talk more about that if it comes up. But I think for all purposes here, it's good that we just recognize we can just solve using the V we previously had. Solve for, that's the V from over there. And you can solve this whole expression. So we'll write over here where V is equal to QBR divided by mass. Okay. So you're going to plug that in, clean up the expression, and you'll get mu naught Q squared V divided by 4 pi R M. Okay. And it's going into like what we talked about. And there's like a right-hand rule associated with this. And I don't know if we went over it, but I guess I'll just am I recording? Yeah, I guess I'll just teach it real quick. So this is like another one, it's like a modification of the first one. Remember, this is that unit vector right here. We're gonna call it like little r, right? And all right, how do I like this. So your pointer finger is going down for V, your middle finger is that R vector, and my thumb is pointing into the page on the inside of the circle for my V vector. So that's like a take on it that I don't know if we're gonna go into it in this class, but in case it comes up, yeah, that's that. But maybe part B is less important than part A in this one. That's kind of yeah, that's kind of like a little bit of a different thing. So sorry, I hope that doesn't cause confusion. Anyway, I'll take pictures and we'll go to the next one. All right, number 8. This one's pretty hard. We have to work with a solenoid, which I don't know how much we've talked about, but a solenoid is basically like imagine like a spring, right? It's like a bunch of coils that has like a current going through it, right? It's like imagine like a spring or like a slinky with a current going through it. So we have this situation here where we have an electron enters in from the left with a given speed, and we know how long it is, we know how many turns are in the solenoid, and we know the current going through it, and we want to know how long it takes for the for the electron to exit the solenoid. So we have an electron like shooting up from the left through this way, and within this solenoid, obviously there's going to be a magnetic field because there's a current that's like spiraling around. And we want to see how long it takes to go that distance L. So I want to establish, a few things. Like we're going to solve part A, like time. Whenever we're asked for like solving time, that's a pretty big giveaway that we're going to need to use kinematics to solve, right? So you have to remember back to 135A. And, well, I guess, yeah, we don't even know the direction of the magnetic field for solving this, but since we're talking about the diagram already, let's just do it. So here we have a current that's like coming out. Like this is a cross section of this spring, right? So imagine you cut that spring in half. The current is coming out and then in, and then it rolls around to the other side. It comes out and then in, and then it like rolls around and comes out and in, etc. Right? So if you do your right hand rule, like when we're like this, we see our thumbs going in here and our fingers are pointing straight. Remember, it's like 90 degrees. And over here too, like you do your thing here. On this side, sorry, it's kind of awkward, but it's curling that way. It's going straight. So your V field is effectively along the horizontal like that. Okay, and that's reasonable because otherwise, like this particle is going to bump into the top of the solenoid. So there needs to be like this vector here or this field that will correct that and let it shoot through. Okay. So we're looking for time in kinematics. So we're looking for this t value. So we have a few things in the x direction, right? We have the velocity in the x direction. And they gave us the angle it enters. We know by the opposite interior here, that's also theta. So we'll say v naught cosine theta. That's the x component of velocity, v naught cosine theta. The next thing is like its displacement, right? So delta x, and that's going to just be equal to L, right? How long it takes to start from that one side it enters to the other side. So L. And then we also have the acceleration in the x direction. Well, there is none, right? The current's the same, so 0. Okay, and then what we're looking for is time. Well, let's say we want to find t. It's equal to what? So which equation? We're going to use delta x is equal to the initial velocity in the x direction times t, and then plus 1/2 at squared. But you know the acceleration is equal to 0, so that whole thing pops out to equal to 0. We plug in the plug in the velocity, plug in the angle there. What was it? 75 degrees. Oh wait, we need to rearrange this actually. So then we rearrange. T is equal to delta x over v naught x, where that's equal to L. Delta x is equal to L, and v naught x is equal to v naught cosine theta. T comes out to be equal to point. Let me zoom in here. T is equal to 0.0007 seconds. Okay, so that's T. Solved. All right, now in part 2, we're asked how many revolutions does the electron make before it exits the solenoid? Okay, so this is where this gets bananas. So if the electron enters, and because of this field, it's like starting to spiral like this, right? So we can imagine it in its centripetal way, right? So we can draw the diagram here like this. We know it's an electron, so I'm going to call it E at this position. And kind of the same setup as on number 7 here, except here we're dealing with the y component, right? Because the x component is purely in the x direction, right? If we were considering that, it would just keep going straight. But we're dealing with that y component. So v naught sine theta is what's going to be its tangential velocity, causing it to do this spiral. And per the same logic we used last time, there's that force FB pointing towards the center. Let's see how well we can see. That's not bad. Okay, and we know that we're going to need to work with that radius r right there. Do they give us r actually? No. Oh, but we can use the period to solve for it. Okay, yeah. So this thing's going in a circle, right? So I'm going to have like its velocity going like that, and it comes right there. All right, this one's actually pretty tough here. So let me write, shoot, I can give you guys the solenoid equation in the worksheets. All right, let me pull up the solenoid equation and show you guys. All right, yeah, so I'll show you the magnetic field of the solenoid when we get there. I think that if I just go step by step, rather than just jumping ahead, will make it easier, okay? So, same setup as last time. We're going to use the second law here. I'm going to call this B Roman numeral 1, okay? And let's just keep things clear here. So we have FB as equal to MAC, right? And we know that whole business with AC is equal to the, right, where AC is equal to V naught Y squared over R, right? And that's because, again, we're dealing with the y component of velocity when we're in this solenoid situation. So this part stays the same. So Q, what's this V? V naught Y. And I'm going to say V naught Y, is equal to this V naught sine theta, right? It's like the same thing. And then cross B. And that equals the MV naught Y, V naught Y squared over R. So I'm going to cancel one of these guys out. Cancel like this. And what I'm going to pull out from here is R is equal to M V naught Y divided by Q B. Okay, So now I have a radius, and with this radius, remember, what are we looking to solve for? We need to find the revolutions it takes before it exits the solenoid. So we're gonna need to work with frequency. Remember frequency from before? So frequency is equal to 1 divided by the period. And if we can express period, okay, so frequency is equal to 1 over the period, right? And we remember from before 135a, the period is equal to 2 pi r divided by the velocity, right? So v naught y. Okay, so now I have something I can plug in for that r position, and then I can effectively find t, and then work to find that frequency. Because the only way I can find the number of revolutions is if I compare the frequency multiplied by the amount of time that it goes through. So again, let me clean this up a little bit. Let me plug in r here. So t then is equal to 2. Oh gosh, all right, I need to scoot over here. So t is equal to 2 pi over v naught y, right? And we can now bring in that r we just solve for down here, right? So mass v naught y divided by qb. Close parentheses. These cancel out. We have this t now, and with this t, we can solve for frequency just by doing a little flip, right? The frequency is going to be equal to qb divided by 2 pi 2 pi m. Okay, so now we need to ask the magnetic field. Like this magnetic field is different. It's in a solenoid, right? So the magnetic field in a solenoid is equal to mu naught n I divided by its length, right? Where that n is the number of loops. So we'll say over, I'll scoot this. I don't want to erase. Scoot this over here, like this. All right, like this. Frequency here, where that b within a solenoid, b is equal to mu naught n I current divided by L. Again, that n is the number of loops. They tell us that's 500. So therefore, we can express the frequency as equal to mu naught I q times n divided by 2 pi mass times the length there. Okay, we're almost done. So having understood this, we can now find the number of revolutions. We'll just call that little n, right? Where little n is equal to the frequency times the time. So, I mean, I'm really running out of room here, but you know, this is known, this is given. This is an electron. This is given. Mass is an electron, and the length is given. Time we solve for in part A. So therefore, you solve for n, and it's in units of revolutions, and it's equal to 5, 4, 1, 6, 2, 0, 1. And I'll say rev for revolutions. Okay. So yeah, this one's pretty tough. Sorry, I was wondering if I should pause and make a. Oh my god, I didn't. Okay, press play. If I should like write the formula sheet down and like make an updated formula sheet, but you guys have yours. I just want to make sure we address solenoids. I'm not sure how much they'll come up, but yeah. So again, what we do is we find time with kinematics. We have to then work to find the radius, right, or this r value, and plug that into the period to find the frequency, where frequency times time, you know, it's like how many times will it spin is equal to the number of revolutions, right? Frequency times time, that equals n right there. So yeah, this one's kind of a lot here. I can clear it up as needed. All right, I'm gonna pause the recording here and take pictures. All right, and oh wait, I didn't erase. 1 second. All right, sorry about that. So now we're just gonna do bonus number 1. This one's more in line to what he provided on the practice exams. You also see that I included like another bonus, which is like a capacitor circuit system. That wasn't included at all, so I'm not going to solve that one. But if you guys want to do it on your own time, I'm happy to give you the answers there. I'm going to focus this recording on what's kind of more topical. That being said, I didn't see the exam, so I don't know like if he's trying to pull a fast one, but he's not probably, and you know, it's just not there. So his emphasis doesn't seem to be on that one. Okay, so anyway, we're dealing with electric potential. So that's, you know, we're looking for the voltage at certain positions. And this is the same situation as number one, and that's how I got those R1 and R2 values. So I'm asked to find the potential at point P. So potential at point P, you know, is equal to part A. Part A is equal to VP, you know, is equal to V1 plus V2, okay? So, you know, it's kind of just plug everything in, right? So K constant, Q1, and then it's how far is that distance R1, right? And then plus KQ2 divided by R2. And that whole thing is, you know, factor out the K, plug in everything, and you'll get your answer as minus 2772.15 volts. Okay, so VP equals VP. Now, kind of the harder part is part B. We're asked to find the total electric potential energy of this system of three charges. And now this is and a third charge is added at where P is, right? So now there's like Q3 here, where Q3 is equal to minus 5 microcoulombs. All right, so now this is kind of a unique setup here. We haven't done this kind of question before. We have to use the equation. Oh my gosh, 1 second. All right, sorry about that. I had to erase. So now we have to use a new equation to find the total electric potential energy. And basically what this requires us to do is we have to take each combination of charges and solve for an interaction between them. Okay, so what do I mean by that? I mean, I have to consider 1 on 2, 1 on 3, 2 on 3, and oh, that's all of them, right? There's only 3 combinations. But sometimes if there's like 4 combinations, you can see how that system grows quickly, right? So there's an equation you can do to determine how many combinations there are. And I'll show you what I mean when I say combinations, right? So let's first say how many combinations there are. You take the number of charges, here I have 3 minus 1. So I'm going to call it N is 3 minus 1, which equals 2. That's the first thing you do. And then you plug this N into this equation, N plus 1 divided by 2. Okay? Now you plug in N here, so that's 2 plus 1, 3, times 2, 6, divided by 2 is equal to 3. So therefore is equal to 3. I'm going to write 3 COM for combinations. There's 3 combinations. 1 on 2, 1 on 3, 2 on 3. And that's how we do it. So we have 3 combinations. We're solving for the potential U total of the system total. And again, I have to consider all the combinations. So first, KQ1 on Q2. And what's the distance between them? Maybe, oh, it's 2 meters. I'm going to call it X though. Wow, that was the nicest X I ever made. And I did it just really quick. You'll see in the picture. It's good. Good stuff. And then plus, now I have to do KQ1 on, what's the other one? Q3. And what's the distance between them? Let's call it, what would I call it? R1? R1. Okay? And then plus, I'm going to write it over here, plus KQ2 on Q3. And what's the distance between them? Well, that was R2. R2. Okay, so now I have every combination of charge interactions multiplied by K divided by their distance between them. I can now factor out K and then have the fun of plugging all of this business in and solving. When you factor out K, plug everything in, your U tote comes out as equal to 0.000361 J. Okay, U tote. All right. So that is the total electric potential energy of the system, given we have this third charge here, right? So that one can be a little tricky. It's a new way to kind of ask the question, so it's worth your time to consider. All right, and now in this second bonus, like I said, I'm going to leave it up to you guys if you want to solve it, but the equivalent capacitance is equal to 2.5. The charge on Q1. Well, where is the charge on Q1? All right, the charge on Q2, I mean, is 2 microcoulombs. The charge on Q3 is 12 microcoulombs. I'm sorry. Charge on Q2 is 12 microcoulombs. That's equal to the charge on Q3 also, and the charge on Q6. And then Q4 is equal to 6 microcoulombs, and Q3 is equal to, Q5, I mean, is equal to 18 microcoulombs. I was doing so good, and I messed up like 15 times at the end. Jeez. Yeah, second bonus, if you want to talk about it, we can talk about it at the review session, but it wasn't emphasized on the midterm review, either worksheets. So yeah, and that's how you solve this one. All right. I had a good streak going there and I messed up at the end. So I hope maybe nobody watched this far. Maybe. All right. Signing off.